Bias means how far you have come in predicting the desired value from your actual value. It is an approach that can ultimately make or break the model in favor or against of your idea. It can also be thought of as a methodological error in your machine learning model due to inappropriate assumptions made by you during the making of the model. Variance is the reverse of bias. It is called the variance when your model performs exceptionally well on the training dataset yet fails to live up to the same standards when running it on an entirely new dataset. Trade-off is simply the tension that exists between the error that is introduced by bias and variance. So if you're somebody who wants to learn about it, you are at the right place. So without any further delay, let's start the video. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Hello everyone. Today I'll be talking about the topic bias variance trade-off in machine learning. So let's just look at the agenda for today. I'll be starting off by giving you a general introduction through a small example. Then I'll move on and talk about bias and variance in machine learning. Further which I'll be talking about bias versus variance, like what are the distinctive differences between these two whenever we talk about bias and variance in a machine learning model. Then I'll be showing you a hands-on using a dataset on Google Colab, and then I'll be ending this presentation by summarizing all the points. So let's move on and dive right into the first part, which is the introduction. Now, whenever we talk about the performance of our machine learning model, we generally divide it into these pointers. Evaluation is always based on the accuracy of the model. With that, it also becomes imperative or important to understand the prediction errors, right? So whenever we are doing evaluation based on the accuracy of how your machine learning model is going to perform, we also check how accurate is your model's prediction, right? Like, for example, how does it perform when we test it with data sets that are independent, data sets that your model has never been seen before, or data set which your model has never been tested on before, right? And then we also talk about errors. So basically, whenever we talk about errors in machine learning, there are two kinds of them. One is the irreducible error, and the second one is the reducible error. So let's move ahead and understand what is irreducible error. Now, irreducible errors are simply errors that are not generated due to noise. As the name suggests, these are errors which are omnipresent throughout your model. Now, let's say even if you are a machine learning engineer or a data scientist who's working in a company, you developed a machine learning model and the accuracy rate of your model is around 90%. You will still have irreducible errors throughout your model. What is very important here to understand is that it doesn't make a difference how perfect your model is. Even if your model is extremely perfect and it performs really well on all the parameters, it will still have a certain degree or a measure of error or noise that cannot be eradicated or removed. So this was about irreducible error, people. Let's move on and I'll be explaining you about the reducible errors. Now, reducible errors are errors which are evident in your model. When we spoke about irreducible errors, these are basically very small errors which you don't actively see in your model, but they are present. Reducible errors are errors which you actively see in your model, right? In simple words, these errors can be improved or worked upon by improving the model. For example, understanding the latent phenomenon, how your model is performing, or checking the fitting. Does your model have any sort of overfitting or underfitting, etc.? This error generally takes place or happens when the output of your machine learning model does not match the desired output and model can be further improved. So now let me start off by explaining you what is bias under the topic bias and variance in machine learning. In simple words, bias means how far you have come in predicting the desired value from your actual value. Well, it can also be thought of as the ultimate approach which can break the model in favor or against your idea. Now, what do I mean by this entire statement, how far you have come in predicting the desired value from your actual value? Well, it generally happens as that in your entire journey of your machine learning engineer or a data scientist, you would be building machine learning models, right? Now, here, the decisive factor would be how will you be able to measure the desired value, that is the desired machine learning model that you wanted, from your actual value, that is the data that you trained it on, or the problem statement which it is based upon. Now, moving forward, one of the straightforward example of this can be your linear regression algorithm. Now, we all learn about linear regression algorithm when we start our journey in machine learning, right? So we basically try to quantify the relationship between two variables x and y as linear. On the contrary, in real life, it just so happens that the relationship between these two variables are not perfectly linear. So what we had read in textbook or wherever we had read the source from, it cannot be entirely correct. So what is this particular term bias? It can be thought of as a methodological error in your machine learning model due to inappropriate assumptions made by you during the making of that model. Now, what do I mean by this entire statement? Well, it is some sort of an error, right? Now, when I say these two words, inappropriate assumption, what I basically mean is these assumptions can stem from various reasons. It can be a human cognitive assumption, or it can be an error in taking some sort of a survey or while you're collecting data. It is always dependent on two parameters, one being the quality and other being the size of your training data set that you're using to teach your machine learning model. Now let's move ahead and understand what is variance. In very simple words, variance is the reverse of bias. It is called variance because here your model performs exceptionally well on the training data set, right? Yet it fails to perform on the same level when you train it or when you introduce a new data set, right? So in simple words, your model is trying to convey you that your predicted values are very far away or scattered from your actual values. This concept is also similar to a concept called overfitting of model on the data set, which is also called as the difference between the model fits when we are using it on different data sets. By different data sets, what I mean here is your usual training data set and an entirely new training data set. Now let's move ahead and understand few differences between bias and variance in machine learning. Well, bias leads to underfitting and variance leads to overfitting of the data. We'll be learning about these two particular terms further ahead in the presentation. Bias is also the measure of difference between your predicted data from your actual data. However, variance is only the measure of how much your target data or your target function will change when you run it on an entirely new training data set. Now let's move ahead where I'll be talking about bias versus variance. So here I'll be discussing one of the most important parts, why your data should not have biases or why your data should not have bias. What is the reason of having it? The first and the most crucial factor to understand here is that bias leads to misinterpretation of your data. Getting rid of bias essentially starts from you, that is a stage where you realize is that the bias that exists in your data is not a cumulative factor of the data and the person analyzing it. It does not exist cumulatively. Now, what do I mean? Now, you can be a person who has done some mistakes or who had certain biases when you were collecting the data or when you were making that data set, right? So, and then there could be an inherent bias of the data also. So that you have to realize that you need to separate these two parts apart. The third and the most important point is it can stem from various sources. As I had already discussed, the sources include humans who would have used uninformative data or incomplete surveys or biased reports and measurements. Other points is human cognitive bias. Human cognitive bias is basically a error. It is some sort of a methodological error or a flaw in your way of thinking or in your way of collecting the data, right? So basically it leads to different kinds of perceptions, or I can say twisted perceptions when you're making decisions. The data here might seem extremely subjective. Now, for example, let me give you a very small example here. You are a data scientist. You are the only data scientist who works in the organization of in a certain organization or a company. You have been given a certain task to make a machine learning model. Now, that model which you are going to make will always have a cognitive bias attached to it, because you will be taking certain parameters according to what you think is right. But that's not what the organization is looking for when you make your machine learning model. Another point is the influence of this bias data in the world of artificial intelligence is huge. Let me give you an example how. So there was a case that happened in the year in 2014 in London, where Alexa started playing songs of its own and started saying discriminatory stuff to the person who owned it. Now here, the word discrimination is also some sort of a bias, right? Because it takes the shape of the data, and that leads to a lot of flaws. Now let's understand why your data should not have variance. One major disadvantage of variance is that you cannot very easily interpret or understand it. It constantly clouds your judgment. What I mean when I say this particular word clouds your judgment is it constantly makes you question your own judgments or your own decisions, which leads to a very messy and irrational data. One example can be in finance teams, variances sometimes can lead to tough questions on the credibility of the business and the finance reports. So now let me talk about why your data should not have variance. Now, one of the major disadvantages of variance is that it cannot be easily understood or interpreted. It constantly clouds your judgment. Now, what do I mean by this particular term, clouds your judgment? What generally happens is it will force you to question your own decisions, which ultimately leads to messy and irrational data. One of the most common example can be in finance teams working across different organizations, different companies. Variances can lead to tough questions on the credibility of the business and the finance reports. Moving forward, there are 2-3 more steps like this, that lead to variance in data. One of them is delaying in time. And the example can be, again, let's say there is an accounts team that works in an organization. So the variance is calculated by accounts team each quarter, and then the information is shared with the upper management or the other hierarchy. However, what's important to know here is that firms or organizations do not wait for the variance and analysis to go on as they constantly function. So delay in time is one of the most powerful blocker which can lead to variances in your data. Again, another point is setting standard problems. Specifications and approximations are fetched from different sources. So the specifications of the data, or the approximations that people are trying to approximate in the data, they can fetch it from different sources, different areas. And they are also affected by human biases. This can also lead to variance, resulting in lousy or incomplete or misinterpreted information. Now let's move forward, where I'll be talking about bias-variance trade-off. Since bias and variance are inversely proportional to each other, let's understand the terms low bias, low variance, high bias, and high variance perfectly. So what do we mean by low bias? Well, low bias generally means that it is trying to propose fewer assumptions related to the target function, which is also related to your target data. Like the assumptions that you make are very few. High bias is just the reverse of low bias. So here it is typically proposing a lot of assumptions to your target function or target data. So basically what it is hinting towards is an inaccurate prediction of your data. So what do we mean by low variance now? Low variance means that your sample data is very close to the predicted data, and there are slight changes in your target function or the target data of your training dataset, the training dataset that you're using to teach your machine learning model. However, high variance means that the sample data is very far away from your predicted data, and you need to make a lot of considerable changes in your machine learning model of the target function of your training data set. Now, let me move ahead and explain you about overfitting and underfitting, and then I'll also be drawing a graph so that you have a better idea of both these terms. Any supervised machine learning algorithm always aims to get a low bias and a low variance model. However, in practicality, in real life, you wouldn't find any ML model with an extremely low bias and low variance. That is practically not possible. Overfitting happens when the model you create encapsulates the noise. What do I mean by encapsulating? Here, encapsulate means captures the noise and the underlying pattern of the data. So this generally takes place when you try to train your machine learning model on a training dataset which has a lot of noise. As a result, these models have low bias and high variance. However, underfitting happens when the model you create does not capture the underlying pattern of the data. So this generally happens when you're trying to train your machine learning model on a data set which has very small amount of data, or you can also say scarce data. As a result, these models have high biases and low variance. Now let me explain you overfitting and underfitting using a graph. So firstly, I'll start off by explaining you overfitting. So as I told in the theory, we'll have a x and y axis, and we have the data which is spread across these axes, right? So let me just draw the points here. Here you will see that the lines are not eventually connected, like the data has a lot of noise. So this also means that there is high variance and low bias. And as I've already explained you what overfitting means, so this is how an overfitting looks like on the graph. Now let me move forward and talk to you about, or explain you, or draw the graph of underfitting. In underfitting, we have the x-axis and the y-axis. But here, what we are having is, again, you have the data points which is spread across both the axes, but we basically have a straight line which indicates towards having a high bias and a low variance. So as I have already explained you, what do we mean by low variance and high biases? When the variance is low, basically your sample data or your target function is closer to your predicted data, and when your bias is high is when the underfitting generally takes place or happens. Now let's move forward and understand the trade-off part, right? So I'll be explaining this in two parts. Firstly, I'll be explaining the why part of it, and then I'll be covering what is trade-off in bias and variance. So let me start off by explaining you the why part of it. In easy words, your model may always have high bias and low variance. And on the other hand, your model can also have low bias and low variance. What's important to find out here is a perfect and optimum balance without doing overfitting and underfitting the data. And that is the reason why there is always some sort of a trade-off that exists in your complexity of algorithm between the bias and the variance. Now, I'll be explaining about what is this trade-off. Well, this trade-off is simply the tension that exists between the error that is introduced by both bias and variance. Since bias and variance are inversely connected to each other, it's always quite impossible, and as I had already talked about it, it's impossible to run an ML model with an extremely low bias and a low variance. So you might expect one of the other parameters to be high. What we try to do is minimize the error, and this is where the concept of total error comes into picture. In order to have a very optimum, perfectly balanced data, we need to minimize the total error between bias and variance. So what is this total error? Well, this is all about finding the right balance between bias and variance, and we need to reduce or minimize this total error. And a right balance will never overfit and underfit the data in terms of its algorithmic complexity. So as you guys can see, this is also the mathematical expression for total error here. So I've already explained what do I mean by irreducible error when I started the presentation, and about variance and bias. Now let's move ahead, where I'll be drawing the graph of total error, since it's always about finding the optimum balance, right? So now I'll be drawing the graph or the diagram for total error. So on the x-axis, I'll have algo complexity, which also means algorithmic complexity. And on the y-axis, I'll have error. So this is also called as optimum. I'm sorry, I think the spelling is wrong. So let me just erase it and write it again. So this is called as optimum balance. Now, how do I draw the variance and bias and the total error? So if I have to show you in a very simple term, this is the intersection point where both bias and variance meet, and there are different data points here on both of these lines, right? So it starts from here, it goes here also, goes here, there, and there. So this is your bias, cap 2, and this is your variance. And this is the part which is called as your total error, right? So since here we are trying to reduce or minimize the total error, so we are basically trying to achieve an optimum balance. And every time, whenever we want to make a good ML model, we always strive for minimizing the total error. So with this, let's move on to the hands-on part. Here I have taken a diabetes dataset where I'll be showing you mean squared error, bias, and variance error on that dataset. So let's get started with the coding. Now let me start off the hands-on. So here I'll be practically implementing the coding, right? So what I have done is I have taken a data set which is already existing, and then I have tried to tinker with that data set a little and try to apply bias and variance. As you can see, the first few steps remain the same. I'm importing NumPy as NP and pandas as PD. I don't really need IO here, so I don't think I'll be doing it. So I don't really need matplotlib also. Then I'm importing sklearn, that is going to divide our data set into train and test split. Then I also need to do linear regression here, and I have to find mean squared error with bias variance decomp. So what is this package? Guys, do you see something different here? Because all of us are used for doing something else, right? So let me just select this part. Basically, this is one of the packages offered by Python to do machine learning activities or daily data science tasks in a very easy way. As you can see, this when I imported this part, this is going to make our coding life very, very easy in spite of us writing a lot of routines and functions. So as I move ahead, since I'm coding in Google Colab, I have to import the file. So these are the 2 lines of code that I always have to write, right? So let me just run this code quickly. Right. Now I'm going to choose my files. So I'm going to choose my file, which is the diabetes dataset. I chose my file. Right. And then I move forward. Now I converted this diabetes dataset into a CSV file and I stored it into the DF. So DF is just the name or another variable name that I have given to store my CSV files into. Now I want to understand what is this data says. I want to see what this data set is about. For that, I have written, in order to see the first few rows, I have written this function or this code df.head. So what is df.head is going to fetch me? Well, it is going to fetch me all the column names which are existing and the first 5 rows, right? Now we'll move forward and then assign this df.value. So I want to understand how the values look like. And then I have named 2 new variables here, which are x and y. So firstly, I have assigned df.values into an entirely new variable that is data. And then I'm slicing this data according to x and y, which also leads us to our next step where we are splitting this data into train and test. So as you can see the code for yourself, when I'm writing the code for train and test split, I have written this as x, y, and the test size I have given as 0.3, which is the optimum way whenever you do write code for data science or machine learning, right? So you basically try to do it on 70% of the training data and 30% of the test data. Moving forward, as I had imported the linear regression package already, I am basically creating a new variable where I'm calling the linear regression function, right? So I'm invoking that function, which is an inbuilt part. And then finally, what I'm trying to do is I have named 3 new variables, which are bias, variance, the short form for variance is var, and then mean squared error, the short form is MSE. And then finally, what I'm trying to do is I'm just writing the same code, which is bias, variance, decomp. So do you see, guys, how your life has become so easy now? It's just 1 line of code in spite of you writing so many routines and functions prior to this, right? So you write this 1 line of code, you implement this in your model, right? And when you move forward, okay, I think it's reconnecting. Yeah. Okay. All right. So I think it's sort of reconnecting here, but it's okay. I'll just run the code accordingly. It's connecting right now. Okay, now it's connected. So this sometimes happens when you're using Google Colab, guys. Right. So once you're done with this part, we move forward and now we want to see the results directly. Now, guys, can you see how your life has become really, really easy? So you just wrote one line of code and you can actually apply and see what is the bias, what is the variance, and what is the mean squared error of your data set, right? So I just wrote this code, print your mean squared error with, one decimal places to the right. You can use 2f or 3f also just to keep tinkering with your code. And finally, I received this result. So as you can see for yourself, the bias is also low and the variance is low. But again, it is not extremely low. So this data is good to go. It is performing exceptionally well on our training data set. Also, guys, I want to end this coding tutorial or this hands-on part on one note. Whenever you're trying to import this particular library, which is from machine learning extension, it's called as a machine learning extension library or package, you need to install it first. And this goes for both of the people. So people who use Google Colab or people who use Anaconda or Jupyter, right? So you need to write pip install mlx tnd upgrade, and then you can use this package directly. Otherwise, it is going to throw you an error. Since for me, even if I delete it right now, it is not going to throw an error because the requirement is already satisfied. So with this, guys, we come to an end of the coding session, or I can say the hands-on part. I just showed you the hands-on using a dataset. Now, with this, we come to an end of the presentation. So let me quickly summarize all the points that I covered in the entire presentation. So I started off by explaining you what is bias variance trade-off and why is it such an important concept that must be included when you're trying to build a machine learning model. Then we understood the types of errors and moved on to the bias variance trade-off. So there were two types of error. One was irreducible error and the other one was reducible error. And then we understood about the bias variance trade-off in machine learning in detail. Furthermore, we also understood about different types of biases and variances, where I made you understand about two of the most important concepts, which were overfitting and underfitting, how low bias, low variance, high bias, high variance happen, and what do they mean, and how they affect their models and why they exist. And finally, this concept is basically very essential and critical for understanding the nitty-gritties or of the behavior of a prediction model. So the next time you are building a machine learning model, do watch out for overfitting, underfitting, bias error, and variance error. Thank you.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.